So, as usual, we have a very interesting lineup of speakers. We'll hear from our own Tarraneh Eftekhari, on a radio source coincident with Superluminous Supernova. And we have three guests: Debora Sijacki, visiting us from Cambridge, on an AGN jet heating of galaxy clusters. And then we will also hear from Sofia Ramstedt from Uppsala, DEATHSTAR. Very challenging name. A new hope for giant winds. It's the first time I've heard DEATHSTAR associated with hope. And then Alex Lazarian, who's well known to many of us from the University of Wisconsin and Madison, exploring galactic magnetic fields with velocity gradients. So we'll start out with Tarraneh.
Can everyone hear me okay? Sounds like it's on. Okay. All right, so I'm going to be talking today about our recent discovery of radio emission coincident with a young superluminous supernova. And I just really want to emphasize that this is the first time that this has been seen, despite previous searches for radio emission around these sources. And so the extended title to this talk really kind of gets at the point that this may be evidence for a central engine, and as I'll discuss, possibly even evidence for a connection between these types of supernovae and fast radio bursts. But before I present our results, I thought I'd give a brief overview on fast radio bursts and the first repeating FRB, which actually motivated the survey that led to this discovery. So fast radio bursts are millisecond duration radio transients. They exhibit these large dispersion measures, which is what we see in the dynamic spectrum here, where the lower frequencies arrive with some time delay relative to the higher frequencies. And these large dispersions are, in fact, much higher than what we expect due to propagation through the Milky Way alone. And so this is really suggesting that these sources do originate from extragalactic distances. So despite a growing number of detections, the underlying origin of FRBs remains a mystery. And this is due to the fact that typical localizations are generally too large to make unambiguous associations. So the overall picture changed with the discovery of FRB 121102. This was the first repeating FRB, which enabled a sub-arc-second localization with the VLA and subsequently the identification of a host galaxy, making it the first and so far only published FRB with a precise localization. And in addition to identifying the host galaxy, the localization also led to the discovery of a persistent radio source co-located with the position of the bursts. And so this is really the first time that there was a bit of context that could provide some insight into the actual sources and progenitors that might be producing FRBs, this new class of transients that up until very recently had more theories describing the emission than there were actual detections. And so following the discovery, Brian Metzger, Ito, and Ben Margalit actually showed that all of the properties of this repeating event could actually be explained within a framework in which FRBs are produced by young millisecond magnetars born in a superluminous supernova or long gamma ray burst explosion. So these are two classes of transients that are believed to be powered by magnetars, and they also seem to exhibit a preference for low metallicity, low mass galaxies. So for example, if we look at the distribution of the properties of these host galaxies and compare them to the host galaxy of the repeater, we can see that the repeater's host is remarkably similar. And so this is really hinting at the fact that they may share a similar stellar progenitor. And so within this magnetar framework, one expects both FRBs and persistent radio emission on timescales of about 5 to 10 years as the supernova ejecta becomes optically thin to gigahertz frequencies. And so the idea is that these transient sources should then be ideal candidates to follow up on the relevant timescales to look for FRBs in a more targeted way than is traditionally done in these wide field searches. And so what we did was obtain ALMA and VLA observations of 32 superluminous supernovae and long gamma ray bursts on timescales ranging from about 3 to 10 years after the explosion. And in addition to searching for persistent radio sources, we also obtained simultaneous phased array observations with the VLA to search for individual bursts. And so I want to focus on one source in particular that has really interesting properties that are actually reminiscent of what was seen from the repeating FRB. So this is the superluminous supernova, PTF10HGI, nearly 8 years post-explosion. On the left here is the VLA 6 gigahertz image showing the position of the supernova in red. And on the right is an HST image of the host galaxy. And what we find is that the radio source is coincident with the position of the supernova to within 0.1 arcseconds. And I should also point out that the same source is not detected in our ALMA 100 gigahertz observation. And so the question is, of course, whether the radio emission is actually related to the supernova or, say, simply due to star formation in the host galaxy or some other phenomenon. But what we find is that most of these scenarios here are actually pretty unusual. And instead, what I alluded to at the beginning of the talk is that we may be seeing evidence for a central engine-powered nebula, and possibly even an analog of this repeating FRB. And so I'm just going to focus on a few of these for the remainder of the talk. So one of the things that we consider is dust obscuration in the host galaxy, simply by comparing the radio-inferred star formation rate to what we find in the optical. And so if we look at the sample of superluminous supernovae and long gamma ray burst hosts, or even just dwarf galaxies in general, we see that there really isn't a whole lot of indication that there's significant dust obscuration in these galaxies. So on the other hand, if we assume that our radio detection is due to star formation, we find that approximately 96% of star formation activity in the galaxy would be obscured by dust. And so this is really suggesting that the radio emission that we're seeing is probably not due to star formation. And this is similar to what's seen from the repeating FRB if we assume that that persistent radio source is also due to star formation. Okay, so it could be that what we're seeing is due to a shock interaction between the outflowing. So similarly, we could be seeing a shock interaction in the form of an off-axis relativistic jet. So in this case, we generate a grid of afterglow models for a range of CSM densities and jet energies in order to trace out the region of parameter space here that's consistent with our 6 gigahertz detection. And as with the non-relativistic case, what we find is that the inferred energies tend to be much higher than what is seen in the sample of long gamma ray bursts. And on the left here, we're plotting 3 representative afterglow light curves, all of which are consistent with our detection. But again, if we overlay the existing limits for superluminous supernovae, we see that those rule out the presence of a similar jet. So that being said, recent work by Ben Margalit actually showed that a sufficiently energetic jet could break through the supernova ejecta. And it turns out that for the inferred ejecta properties of this supernova, that minimum energy is about 2 times 10 to the 53 ergs. And so we do find that our inferred energies are consistent with that scenario. And so it could be that what we're seeing is an off-axis jet, which again would point to the presence of a central engine. And finally, that brings us to the last model we explore, in which the radio emission is due to a pulsar wind nebula powered by a young magnetar embedded within the supernova ejecta. So this is based on modeling done by Ben Margalit and Brian Metzger to explain the data for the repeating FRB shown here. And in particular, they showed that the persistent radio source can be explained by a magnetized electron ion nebula, which is produced as the magnetar releases magnetic energy from the stellar interior, inflating a compact synchrotron nebula behind the expanding ejecta shell. And what we find is that the same model can be used to explain the radio emission from our source for reasonable model parameters. And so here I'm showing 3 unique models based on the allowed range of values for the spectral index that we find in the radio. And also our ALMA non-detection. So in the first case, we find that the same exact model that can explain the persistent source from the repeating FRB can also explain our data here with the magnetic energy simply scaled down by a factor of 20. And then these 2 models here correspond to the 2 limiting cases for a synchrotron self-absorbed source. And as I said, that's one of the possibilities is that the emission is self-absorbed based on what we find in the radio from the spectral index. And that would really be pretty exciting because this is the only model that can accommodate self-absorbed SED in this part of the spectrum. And finally, the last thing that I should point out is that we can estimate the free transparency timescale. So essentially the time at which the supernova ejecta will allow the transmission of radio waves. And we find that this is at about 5 years. So again, consistent with our detection at 8 years. So that is all to say that we're still not really in a position where we can definitively say what's powering the radio emission. Additional observations will really be critical for constraining the source of the emission. And I've just listed some of the observations that would help here. But I'd say in the meantime, it's definitely an interesting source that shares a lot of similarities with the repeating event. And so I think it's worth considering that they may share a common origin. And I'll end there. Thank you. Yeah, so there has been some work led by Matt Nichols showing that the rate of FRBs could be consistent with the rate of, say, long gamma ray bursts and superluminous supernovae if all events are repeating and you take into account some active duty cycle.
You mentioned that you could sort of rule out that this was just the interaction between the supernova and the shock because it was lower velocity and higher luminosity than other examples. But could you get that if you just had, maybe this had a much higher density than the other things, so you have a lower shock velocity and it'd be brighter, possibly? Is that possible, or did you look at that?
So if you had a lower shock, a higher density and a lower shock velocity.
Right, so this one just experienced a lot more mass loss or something.
Right, I see. So yeah, we didn't look at that too closely. So this is very much just in the sort of 1 BC context. That would be interesting.
Do you have polarization?
We don't have polarization. So we don't have polarization calibration for our VLA observation. Yeah.
No. I think we should just wait a second. The last time we took it a while. Is it on the slide? Okay, so thank you very much for giving me the opportunity to speak today, and apologies about my voice. So I want to tell you something about a very recent work we did on AJ and jet heating in galaxy clusters. This is together with my postdoc, Martin Byrne, back in Cambridge. So essentially we know in galaxy clusters we have a really very firm and overwhelming, I would say, observational evidence that there are supermassive black holes in the course of these systems, and that supermassive black holes are inflating relativistic jets, and these relativistic jets then propagate, interact with the surrounding intercluster medium, inflate what we called radial lobes or X-ray cavities or just bubbles, which people like to call them, and these radial lobes are thought to be able to thermodynamically affect the intercluster medium significantly. However, the way how this happens, it's not understood at all. There have been many theoretical papers over years to try to tackle this problem and to infer which is the physical mechanisms that transfers the energy from the black hole jet to the bubbles and ultimately into the intercluster medium. And this is a really kind of a fundamental problem because this affects global galaxy cluster properties, and it also affects what can we learn from galaxy clusters about the cosmology. So some of the ideas that we have been floated around is that it's the sound waves that transmit the energy, or it's perhaps the weak shock, or it's the gravity waves, or perhaps it's mixing of this bubble material with the surrounding ISM, or perhaps these injections of these bubbles into perhaps with intermittent jets or jets with varying power can drive the turbulence in the central regions of the cluster core, and that can be spread out and heat these regions. However, we don't have really a compelling theory, so all these options are open, including some more extreme examples like cosmic rays, circularization, and so on and so forth, magnetic draping. So what we have done on this recently, we have developed a really new numerical technique to try to launch hydrodynamical, so this is no MHD simulations at all, rather simple setup, hydrodynamical jets in galaxy clusters and see what we can learn about this problem. So this is just an example of our numerical technique. We adopt a special refinement in the vicinity of supermassive black holes such that to allow us to drive these really elongated jets that are propagating to large distances. Without our technique, we would just get some hot blob in the central region. So these jets, we can now zoom in a little bit. So this is the extent of the jet itself. It's 200 kpc across. And what we can study there is quite in detail the velocity structure of the medium, the streamlines, the density, vorticity, which is very important for the generation of turbulence, and obviously the temperatures, peak shocks, and so on and so forth. So we have first explored this technique in simple isolated setups of galaxy clusters where we have inflated these jets in the central regions of the systems in the cases where the cluster just sits in hydrostatic equilibrium, but then we have slightly complicated the picture and we have introduced the substructures that can stir the ISM, introduce extra motions. And this is what you get once you stir the ISM with the substructures. You actually get much more messy structures, not clearly defined jets, and the lobes do also move around. And then you can do something which X-ray observers always like to do. You can construct what is called unsharp mask luminosity map. So you're trying to pick up actually features that are away from the average luminosity of the source. If you have an isolated jet, you can really pick up very quickly and easily here the X-ray cavities, and here you have actually the sound waves that come from the injection of this jet. If you have a messy ISM with a lot of motions, the picture becomes actually much more tricky to untangle. So what we have done, we have compared this type of simulations with really puzzling observations that recently came from the Hitomi satellite of the Perseus cluster, which have claimed that the motions of the ISM in the central region of the Perseus clusters are really quite quiet, and that the ISM is not turbulent at all. So we have tried to compare our simulations with that, and if you just focus on this second row here, which is our simulations with jets and substructures, and if you degrade it to the Hitomi resolution, you find actually a rather similar picture. You find that there is some velocity gradient in the central region of the cluster, but it's not too large, so it's from like -100 to 100 kilometers per second, and actually we don't find significant level of turbulence at all, even though we have a very vigorous jet in this system. So what we then did next is to try to incorporate all of this in much more realistic setting. So we have performed full cosmological simulations of galaxy cluster formation as shown here. So this is a large-scale view with a filament. The red circle indicates the virial radius. And in this system, at low redshift, we have ejected at very high resolution on the sub-parsec scales a jet, which we then let propagate through this messy medium of a galaxy cluster. So there is an image showing you how this jet looks like, a volume rendering of the jet. These are all streamlines in the intercluster medium. And now I want to focus actually on these little rectangles which shows different zooms. So one is to tell you that this jet actually is propagating perpendicular to a cold disk structure which is entirely rotationally supported. And this is quite reminiscent of the ALMA observations of some of these systems where these jets are also found. Second, I want to highlight the exquisite resolution that we achieve within the jet slopes themselves. So this is shown here. This each little cell is individual resolution element of the simulation, and this is how the resolution is then degraded when we go away from the jet lobes into the ISM. And finally, this resolution permits us then to study with quite great detail the streamlines that form. So the jet is dominated by the bulk motions, but then you can see all these turbulent motions now for the first time in cosmological simulation. We can study with this detail, and we can study then the turbulence that is generated here, and we can study how far this turbulence propagates into the interstellar medium. So just to kind of slightly show you a fudged plot, this is an observation of a real cluster, and this is our mock view of an X-ray emission in blue, like mimicking the colors of the simulation, and pink is where our jet is. So with the morphologies of these simulated structures, we are finally getting closer to what observations are trying to tell us. So here is really the main plot. This is the interpretation. So what do we want to learn? We want to learn a fundamental question: where does the energy go? So we put the energy entirely in the kinetic form in the jet, and this is shown with this red line here, which is showing energy in different components as a function of time. So initially the jet is dominated by the kinetic energy. However, if you look at the top, this plot here, this is showing the pressure differences within the jet region itself. And you can characteristically see all these little pressure amplifications along the jets, the so-called sometimes hotspots, and these are actually internal shocks in the jet, because the jet power and the way how we inject the jet varies as a function of time. So the faster component in the center, when it's injected, can hit the slower component, which is propagating further out. So we have a very efficient thermalization of energy through the shocks that reach Mach numbers from 2 to 8 within the jet, such as that this red line quickly thermalizes into this blue line, which is showing the total thermal energy of the jet. So this we see then while the jet is getting inflated, and this is this gray area, majority of the jet energy content is thermalized. In this form, but then something interesting happens. So you should focus on two things at the moment. So one is the PDV work that the lobes do as they expand through the medium. So the PDV work has been invoked classically as one of the mechanisms how you can transfer the energy into the SM. Some of the problems of the past work have been that these jets have been injected too vigorously, and they led to really large Mach number shocks, which is clearly not observed. So you can see here in these plots down there, these are encoding the Mach numbers that not happen in the jet, but happen in the interface at the bow shock between the jet and the ISM. And there we, at the early stages of the jet inflation, we see moderate Mach numbers of order of 2. At the late stages of inflation, actually there are no stroke shocks at all. So this is a really relatively kind of mild process. So the PDV work then leads to compressional heating and lifting the material that was in the ISM as the lobes propagate away from the central region. And this is one of the very important components, how the energy from the jet lobes is transferred into SM. The second component, and I've finished there, it's actually the mixing of the lobe material with the ISM, and this is not due to the fluid instabilities, as has been advocated in the past. It's actually because the cluster weather, the substructure motions, are able to disrupt the lobes. And we advocated these two very simple channels can actually solve the overcooling problem in galaxy clusters. Thank you. Yes, especially, I mean, if you look at FR2 sources, the very powerful radio galaxies, you can find that the lobes just shoot out of the galaxies and would not affect the galaxy properties. What we have, so then the issue becomes much more interesting, whether you are affecting the surroundings of the galaxies in these systems. But what I have been mostly focusing here is in a classical FR1 type of sources.
Debora, matter of physics.
Yes.
This PDV work.
Yes.
Has always confused me.
Yes.
PDV work is an adiabatic process.
Yes.
It's not creating any new entropy or whatever.
Yes.
Whereas, the cooling, the X-rays that you see,
Yes.
they need an actual source of entropy.
Yes.
Something has to actually heat the gas.
Yes.
So does PDV actually contribute to the X-ray emission?
Yes, so this is a good question. So there is a little bit of I agree with you, misconception in the field. So two things that are happening. The process is not entirely adiabatic. So there are some weak shocks, and there is some dissipation of the sound waves. We can argue how this happens, right? That's one. And the second is not really, we call it PDV work, but you are displacing the medium. So you are working against the hydrostatic equilibrium model that you have. You're pushing the gas up and you're pushing the gas back in. So you're inducing mixing, and this is a reversible process by shooting the lobes. So these are the two things that help you.
Okay, the mixing part I understand.
Yes.
It's the PDV part.
Yeah, but you have a bit of compressional heating because it's not fully an adiabatic process.
So you really need this sort of maintenance mode feedback in cool clusters. But these
Yes.
are also the clusters that have the least cluster weather. So how do you sort of balance those two pictures?
Yes, that's a really interesting point. So I think further simulations are needed to answer this. So we have to kind of gauge the occurrence of how often you can displace or disrupt the lobes and the frequency that happens and how that helps the heating process. And this is what we want to do next.
Is this on? Yeah, it's on. Okay. Thank you. Just get... there it is. Okay, so I'm going to do a little bit of an advertisement for a project that I'm running on ALMA. For the first 2 years of this project, our biggest accomplishment was to make a title that would make the acronym DEATHSTAR. The full title is actually Determining Accurate Mass Loss Rates from Thermally Pulsing AGB Stars. So if you pick out the right letters that you want, you can make it into DEATHSTAR. And also, of course, the awesome logo, which is not made by me, but by one of the students in our group. So I put the subtitle, A New Hope for Giant Star Winds. Now, why do we need a new hope for giant star winds? Well, as I'm sure you know, the winds of the AGB stars is one of the main uncertainties of stellar evolution calculations. And the problem, this comes down to several things, but one is that even like the best observational estimates of mass loss rates that we have uncertainties of the order of a factor of 3. And this is too big to provide meaningful constraints for the wind models that are also developed at my university. So what we're trying to do with this project is to push down the uncertainties of the observational estimates. So just to set the stage a little bit so that you know what I'm talking about. So you have a giant star. This star is on the AGB, is pulsating, and it's throwing out material around it. This creates a wind. You will have to come to my talk this afternoon if you want to know the details of how this wind works. Over time, this wind will create this huge expanding circumstellar envelope. Now, to observe the wind or to observe and determine wind parameters, it's tricky to do it directly where the wind is formed. Instead, what we do is that we observe the circumstellar envelope, which will give you the wind evolution for like the last thousands of years or so. And then we trace that back. So then we get like a mass loss rate. Either you have unresolved observations and then you get an average mass loss rate over the time of the creation of the envelope, or you have resolved observations and then you can actually map the mass loss rate history. All right, so this is the current status from CO line observations. So this is from the circumstellar envelope gas. This is what we know from observations. The different colors mark the different types of AGB stars that we have. They are different chemical or spectral types. So mass loss rates range from a few times 10 to the minus 8 up to almost 10 to the minus 4 solar masses per year. Typical wind velocities are of the order of 10-15 kilometers per second. And this is what the correlation between mass loss rate and wind velocity looks like. So this is what is used to constrain the wind models, essentially, how these two parameters correlate. So maybe I should say that. So the velocity is very well constrained. This we just measure from the width of the lines. It's of the order of plus minus half a kilometer per second, but it's this, the y-axis, that is the problem. Right, so how is this done then? Yes, so we do radio observations of rotational transition CO lines. This is a plot showing you the contribution from different lines at different times of the circumstellar envelope, assuming that it's constantly expanding. So you can use, like the lower transition lines will probe the outer layers, and then the higher you go in transition, the closer to the star you get, essentially. And we usually go up to 6 to 5 because then we're sure that we're still in the region where we have a constant acceleration. If you go further in, you hit a region where you have an acceleration region. And that makes the models, we can do that as well, but this is just to simplify the calculations a little bit. So now this is the nicest, one of the nicer examples that we have. So the histogram is obviously the observations, and the red is the model for a nearby high mass loss rate carbon star. So this gives us, by fitting the lines, we get the mass loss rate and the temperature distribution of the circumstellar gas. Now, we don't know the size of the circumstellar envelope from this. So we have to assume something, so that what we used and what is used by everybody who does these types of estimates is a photodissociation model from 1988. So it's pretty old and outdated. And that will give you the photodissociation radius of the circumstellar envelope, so the size of your CO shell. But what we see when we use this assumption is that for many of our sources we run into trouble. So this shows you that our model, assuming this radius, gets resolved lines while our observations are not resolved. This means that the radius that we put into the model is way too large compared to the size of the shell. And this is one of the main uncertainties that we have now in our calculations. So we want to solve this problem. So what we do is that we map it. We measure it directly. So the DEATHSTAR project is about measuring the sizes of these circumstellar envelope. And for the south, we're using ALMA, and for the north, we're using Plateau Début data, so NOEMA, before it was upgraded, and we will apply for more time on NOEMA once it's done. So what we have is 162 nearby AGB stars that we have mapped. They're all closer than 1 kiloparsec, and we believe that the sample is complete out to about 500-600 parsecs or so. And we're mapping all of them in 2 CO transitions. So the first aim of this project is to improve the mass loss rate estimates, like I said, but the second aim is that this will help us find spherical sources for follow-up observations. It gives you a lot of data. So far, we have only worked through 42 of the ones that are observed with ALMA, although we have observed about 100 stars. And I will give you some very tentative and vague results from that. So what we find is that the assumed sizes are different from what we measure, or the other way around. We measure sizes that are different from what this old photo dissociation model gives us. I cannot say, what we would expect is that they would be smaller, but it's not always the case. Sometimes they are smaller, sometimes they are bigger. And it's not completely unexpected that it will change from source to source, because they will, of course, be in different environments, and the photo dissociation in different environments will be different. But this still has to be worked through for all the sources before we can say anything conclusive about what it looks like. Anyway, we don't need it to go in one direction. We just want to do as accurate estimates as possible. It will have a big impact on the estimated mass loss rates, especially in the optically thin cases, because then the size will correlate almost linearly with the mass loss rate. And this, in turn, will have a large impact on the estimates of the yields. And then, for the other aim that we have, is that we find that about 1/3 of the sources are clearly not spherically symmetric. This is important for the formation of PNs, for instance. How do you form aspherical PNs? And when I say not spherically symmetric, I mean something that is clearly distorted, like you cannot model it with a spherically symmetric code, something that has like a torus and an outflow, or blobs, things happening in different directions. All right, so this was my final slide. So this is very much work in progress. I hope that you will stay tuned, and we will come out with more results eventually. Thank you.
Question about the asymmetry.
Yes.
Possibly one source of asymmetry is that if the ultraviolet field is not likely to be locally isotropic, there'll be a closer Sophie association.
Mm-hmm.
But that would not produce torus like.
No.
It would be like a bite out of one side.
Yes.
So do you see any of that?
I'm not at the stage where I see that in my own data. There is quite a lot of work on bow shocks that you see in these stars. So this is when the star moves through the ISM and you get like a huge arc like this. But this is usually at larger distances than the CO. Yeah.
Are any of these stars binaries?
Yes.
Interaction?
Yeah, so it's problematic. So I will talk about this this afternoon at the colloquium. So it's very problematic to find binary AGB stars. I mean, that you will know that it's binary because you have a super bright star next to something that is not so bright, perhaps. And you also have the big circumstellar envelope. So what we did with ALMA before this project is that we did a sample of known binary stars where we know that it's so like Myra and R-Query and a couple of more sources. And the idea is that these stars can then be used as templates for the ones where you don't know if it has a companion or not, because you can use how the wind has been shaped by the companion and use that to infer that it has a binary companion. This is tricky, as I will come back to later today, but that is one way of doing it.
Any additional questions? Oh yes, go ahead.
Do you see any correlation on where the position of the AGB is on the AGB track, or the evolutionary state, and the radius you measure with ALMA?
We did not look at this. So in principle, okay, so there is this idea that the mass loss rate should increase as the star evolves on the AGB. So the longer it is on the AGB, the higher the mass loss rate will become. And that would lead to a larger circumstellar envelope. So this is for sure something that we can look into. The question is if you believe the first assumption. But yeah, we can measure it, yeah, for sure.
Any additional questions?
Thank you. Do you want this?
No,
Oh, I have a better pointer.
Fourth and final speaker for this lunch is Dr. Lazarian from the University of Wisconsin at Madison.
I forgot the title of my talk, so it was a bit different, but it's the same subject. Yeah, there will be no Darth Vader in my talk, just very mundane magnetic fields. So, and actually last year I was giving a presentation where I was discussing the theoretical foundations of the technique, which now I'm going to discuss practical results. And just to advertise, I would say that these are results where textures are showing polarization from Planck. And this is results which show, again, textures, but this is Galfa 21 centimeter. And you see very good correspondence. Here you see polarization from blast pole, textures show, and this is from ground-based CO13. So this is my team of graduate and undergraduate students who are enthusiastically working on this project, and I will discuss only a small part of this rather extensive project. First of all, magnetic fields. Interstellar magnetic fields, we know that they are important for star formation. They are important for cosmic rays physics, and Ramesh will tell us many more things where they are important. At the same time, for people who are not interested about this galactic stuff, what is galaxy, right? They are interested about cosmology. It's still very interesting because these magnetic fields are interfering with CMB search of enigmatic B modes. Well, The new technique is based on rather simple understanding of turbulent motions in magnetized media. And I can show this with this pens. I like this analogy with the pens. So magnetic fields are like these pens, and it's difficult to bend them. But what we can do, we can mix them up. Why it can be problematic? It can be problematic because you can create knots, because they are long, and they will be, when I'm mixing here and randomly mixing there will be knots, and this could stop this motion. However, some years ago, actually, last century, last millennium, together with Ethan Wishniak, we found that turbulent eye connection can resolve this knot. So this is a simple picture of this. We have plasma entrained on magnetic fields. These magnetic fields can mix up, as I've just shown, but turbulent eye connection resolves this knot within 182 nova time. It was a prediction, and it was proven by numerical simulations. And as a result, all these eddies are aligned with the local magnetic field. And as a result, the gradients of velocities corresponding to these eddies will be perpendicular to the local magnetic fields. And therefore, measuring by these gradients with spectroscopic means, Doppler shifts, we can measure the direction of magnetic fields. This is a simple numerical illustration. These are the contours of equal velocities with numerical simulations, and you see velocity gradients are perpendicular. This is the illustration in terms of the observational data, because we need to measure this observationally, and this is the channel maps, velocity channel maps, and again we see that these gradients are perpendicular to magnetic field. This was last year work. Let's go about this year to this year. This year, for example, we applied this to Perseus. And this is Planck results. This is direction of Perseus magnetic fields with Planck. And this is what we get with the ground-based data, FISI-RAO telescope. And you see, there is a good correspondence between these directions, but there is more to that. Look, we used this bow tie mark. These directions are just directions. But here we have also the, due to this color coding, we have magnetization. Gradients give us not only the direction of magnetic fields, but also the magnetization. And it's a pointwise distribution of perpendicular to the line of sight magnetic field. And using Chandrasekhar-Fermi technique, we see that Chandrasekhar-Fermi, for example, from Planck, pretty similar to what is the mean value for the distribution for this directions of gradients. But here we have a distribution. We can see the distribution of magnetic fields over the image. This is Planck data, and this is 21 centimeter data. These are low latitudes, and we see good correspondence. Planck data at this latitude has a good signal to noise. Let's go to higher latitudes. At these ranges, you see there are funny shapes of Planck data, and it's known to be dominated by noise. But the maps that we are getting with H1 are giving us a good structure. We can get on not only the direction, we can also predict the degree of polarization that is expected from dust, and this is important for cosmological studies. For example, this is polarization percentage of Planck. This is our data. We are working on improvement, and I think we will improve it. It can be of much higher resolution than Planck, and it can be at the latitudes where Planck is not able to get us the results. These are results from VLSC. VLSC is one of the interesting clouds. Near recently it was studied with blast pole. Blast pole provided this 2D picture of the magnetic field directions. This is what we got using publicly available spectroscopic data, using CO13, CO12, and H and C. What do you see here? We are getting three-dimensional structure because these different species sample magnetic fields and different depths. So in general, we have good correspondence, but we get more with ground-based observations publicly available. We can get also something else. We can get three-dimensional structure of magnetic fields in the galactic disk. And this is what is shown here. This is our sun, and this is the plane at which we measure magnetic field direction. These are directions of magnetic field. They are changing. But there is something interesting here. There is vector length is proportional to magnetic field. So we are not measuring only magnetic field direction. We are magnetic field strength distribution. Okay, you can say, wait a minute. You can draw anything to us. How do we believe you? Right. So, well, it's a reasonable question, you know, how to keep theorists honest. Okay, there is a possibility. There is starlight polarization, which is measured. It's an independent measurement. So we took our three-dimensional magnetic fields structure and predicted polarization of the stars and compared to the measured polarization. And this white dots correspond to essentially perfect result. Can we do more? Yes, we can do more. We can do something where polarization is not likely to give us any time in the future. Consider high velocity cloud. This is a Smith cloud, and if we wait a while, we'll see this Smith cloud as we change the velocity. It's only seen in PPV space, position velocity, because its column density is so small that its polarization from its dust is negligible. Oh, this is last. Okay. This is what we get with our technique. And actually, this wrapping structure that we observe is also consistent with the earlier studies by Faraday rotation. We get, as I mentioned, also with other clouds, not only the directions, we also have the magnetization, the strength of magnetic field. And this is consistent also with the Faraday rotation that was studied. Now it's really clear that we can study many clouds, and these are the comparison of what we are getting with our technique with Planck data. And this is my last slide. So the new technique can give us three-dimensional distribution of magnetic fields, and these are different ways how we can do this. We can use either galactic rotation curve or use different species. You can say what other people in this group are doing. There are sister techniques that we are developing, and these are also ways of studying magnetic field using, for example, synchrotron. Thank you.
One object where we actually have a lot of information about magnetic structure is the solar corona. And does the analogy with the solar corona help test any of this, or is the regime that it's not
We have not yet studied solar corona because my field is interstellar media. But I'm in touch with people who plan to do this for solar corona. I don't know how it will work, but it's an interesting possibility. We studied for the molecular clouds. We studied for H1. We have already studied for SMC, LMC, for Magellanic Bridge. And we, with interferometric data, hope to go to nearby galaxies.
Have you compared your nearby magnetization maps with some of the low-power maps at different Faraday depths?
The issue here is that we're measuring the perpendicular component of magnetic field. Low-fi is mostly this parallel component of magnetic field. As a poor man's solution, we're using this comparison with the Faraday rotation for Smith cloud, where we don't have any information otherwise. For the perpendicular component, we have the information from, for example, starlight polarization, as I showed. So I feel that it's a more reliable test at the moment.
And the information from the magnetic field vector maps be translated into Stokes, Q, U, etc.
Again?
Can you get polarization maps directly from?
Yes. Yes. That's what I was showing earlier. Just a few slides. This is, for example, this is the degree of polarization that we are getting, but the previous maps.
Just linear polarization.
Pardon?
Just linear polarization.
Yes, linear polarization. Everything is linear. Yes, no circular polarization. There is someone here.
Yeah, so when you were showing the predictions of the polarization stars, it looks like the match was the best in the kind of outskirts or lower density regions, and maybe like some of the denser stars in the
okay. Are you talking about H1 or? Okay. I'm sorry. It's here, for example.
Pardon? You were predicting what the polarization of stars should be.
Polarization of stars. Here. Okay. Yeah. There are some interesting regions, and we actually know what is happening here. It's due to the fact that these Stokes parameters are additive in a different way compared to the gradients, because gradients have vector additive quantities, and the Stokes parameters are different. We are working on improving this by using this pseudo Stokes parameters, and I already showed some of the new results which I think can overcome these problems. And also, you should keep in mind that this is H1, and in some directions you have molecular clouds. And in this case, the polarization that is measured is mostly from molecular clouds, while we are sensitive only to H1 component. John, yeah. So,
by opposite, should I find you?
I just was talking with Ramesh, and we discussed a meeting for 5 minutes because I would like to introduce a very good postdoc to him. And after that, I'll come. You are on the 3rd floor.
3rd floor.
Yeah.
It was crazy. Like,
Let you down by having compared to me.
No, it's fine. It's fine.
Digging yourself in a hole there, Keep on digging.
I was being nice.
Thank you.
Okay, thank you.
How long are you visiting for?
Pardon? I'm not visiting Harvard. I'm just passing through. I will be leaving. Yeah. No.
Oh, you're leaving?
I will talk with Ramesh and then I will leave. But I will be coming in the morning tomorrow.